For today, I'm very honored to invite my postdoc advisor, Sid, to be, we'll have a fun interactive Q&A with him. So let me introduce him formally. Siddhartha Srinivasa is the Director of Robotics AI at Amazon, the Boeing Endowed Professor at the Paul G. Allen School of Computer Science and Engineering at the University of Washington, and an IEEE Fellow. Before joining UW, Sid spent 18 years at Carnegie Mellon's Robotics Institute, where he founded the Personal Robotics Lab. Sid is a full-stack roboticist with the goal of enabling robots to perform complex manipulation tasks under uncertainty and clutter with and around people. At Amazon, Sid's team owns autonomous manipulation, autonomous mobility, and human-in-the-loop AI at fulfillment centers. Sid has built several robots: Herb, Ada, Chimp, Musher, written software frameworks, OpenRave, Dart, and various Best Paper Award-winning algorithms, CBR, RRT, Chomp. You have read a couple of papers in the course, this Bitstar, Legibility, etc., which are now used extensively by roboticists around the world. In fact, in my lab, one of the projects, like the robot-assisted feeding project, is a brainchild of Sid. And so during my postdoc, I started working on that. Now I'm continuing this. So thank you again for submitting questions. So the way we'll do this, we have 3 sets of questions. Some are generic questions. Some are robotics, like broad robotics related questions, as well as some are robot manipulation, specifically robot manipulation related questions. And so I have an impressive list of questions here. So I'll start with the questions that I have. But at any point of time, if you have any questions, please raise your hand, and then and you can ask directly. All right, Sid, I think let's get started if you're ready.
I'm ready.
Awesome. So yeah, Sid, to start with, maybe if you could share with us a little bit about your personal journey. Like, how did you decide? How did you get started on robotics in general and robot manipulation in particular?
Oh yeah, first of all, thank you so much. It's such an honor to be here speaking to this very, very distinguished audience. You are all the future of robotics. I'm just here to keep the lights on and make the coffee until you all solve all the really hard problems. So super excited, and I know one of the things that I derive a lot of joy from is talking to students and teaching, because I think it's what keeps us sharp. Our dinner time conversations at home with kids are also around robotics and algorithms, and if I can explain my work to them, then I feel like I've learned something. So with respect to my journey, I think I wish I could say that I was born with the desire to do robotics, but really I actually saw my first robot only after I started my PhD at the Robotics Institute at Carnegie Mellon. So this is way back in 1999. Clearly, they had very low standards for PhD entrants back then if they took me. And I think my background was mostly in mathematics, mostly in fluid mechanics. I wrote a lot of code. I started writing code when I was about 8 years old. I wrote video games. That's what I did back in the day with really, really tiny processors and assembly language. And I feel like that combination of mathematics and fluid mechanics and the ability to write code really was the foundation and helped me a lot to embrace robotics. And then I also was fairly hands-on, and my grandfather had an automobile factory that he used to run, and I would go hang out and change the ball bearings and grease stuff. And so I felt very comfortable building things. And so I think I just happened to acquire the skills needed to be a roboticist fairly accidentally, I must say. And then I showed up at the Robotics Institute, and then I realized that actually what I know can be extrapolated into this space. I think one thing I'd also add is that there's no real textbook in robotics. Of course, there are a few, and hopefully, I'll write another one. but I think it means that the barrier to entry is low, right? My wife is a molecular biologist, and she spent the first 3 years of her PhD learning the tools to be able to do the research that she had to do, right? Whereas, as you all know, that barrier is much lower in robotics. You can sort of show up and start hacking robots. And I think that's an incredible privilege that we have, that the barrier to entry is low, and that we're still, the concern, of course, is that we're still sort of in the Wild West. Like, things haven't been formalized. The textbook of robotics is being written, and hopefully some of these chapters will be written by you all. But I think it is indeed quite a privilege that we can just start building robots and experimenting with them without having to spend several years mastering the skills even to get our entry into the door.
Awesome. Particularly, Sid, I mean, robotics is so broad. What makes particularly like robot manipulation interesting to you?
I've always been fascinated by robotic manipulation, and I think it's, there's a lot to it, right? It's what we're really good at. Got these hands, and they do amazing things. I also find it fascinating to ask the question why. Like, a lot of my work stems from asking, like, why do you curl your hands around the coffee mug when you pick it up? Or why do you place things in a particular way? Or why is a particular phenomenon happening? Like, why do we sort of do this dance of signaling when we move past each other, in a walkway? And I think that why, to me, is the essence of trying to get to discovery, right? And I find robotic manipulation particularly incredibly fascinating for two reasons, right? Like, one reason is humans are so adept at it that we do it so effortlessly and naturally. And I think another reason is that if you give a human being, even if it is a relatively novice human being, the same control authority to control a robot, let's say teleoperate a robot, and the same visual feedback or sensorial feedback that the robot has, then a human is able to perform remarkable feats of manipulation with this robot, right? And you've seen you can see videos of like Da Vinci robots, these little surgical robots, and people do amazing things. They peel a grape, they tie shoelaces. People with 2 prosthetic hooks are able to tie a shoelace or light a match and things like that, which suggests to me that the challenge is not necessarily in the hardware, but in the intelligence, like the intelligence that actually drives that hardware to do interesting things. And that's what motivates me a lot about manipulation, is that the fault is entirely mine. I am the writer of the algorithms. The fault is entirely mine that these robots with such amazing nascent abilities are incapable of autonomously performing these tasks. And that's an affront to me, and that really drives me to continue to invent and discover in manipulation.
Awesome. I remember when I was in the faculty job market, you had you're giving me some suggestions on what kind of how to prepare, right? And like what kind of questions to prepare for. So I'm going to ask one of these questions back to you now.
Oh no.
So
thankfully I'm a tenured professor. I don't have to look for another job for the rest of my life, but go ahead.
Yeah. Over the years, you have done so many incredible projects. But if I were to ask you to choose 2 of your projects that you are most proud of, your favorite projects, what would those 2 be?
I see. Well, thank you for putting me on the spot. I'm going to sort of paraphrase by saying that, like, all of my projects are like my children, right? So asking me to pick my 2 favorite children out of like the 15 or 20 children that I have is mighty unfair, right? I do love all of them in different dimensions, but if you had to make me choose along particular dimensions, right? Like not in an absolute scale, nothing is Pareto dominant in the absolute scale, but there are certain projects that I love in certain dimensions. I think for me, and I'll talk about it one from an algorithmic point of view, and I'll talk about the other one from a more like programmatic point of view. I think one of the actual algorithmic advances that I particularly have enjoyed. There's several of them, but the one that I particularly enjoy was some of the work I did in functional gradient optimization. This algorithm called CHOMP that I invented back in, I don't remember, 2011 or 2012. And actually, what's interesting about it is more than the algorithm itself, which was mighty clever and cute. It was the environment in which it was created, right? If you rewind back to 2010 or 2011, many of you were like, in elementary school back then, probably. There was this pervasive attitude that rapidly exploring random trees, these sort of like sampling-based algorithms were the only way to solve motion planning problems, right? I was perplexed by that because these are not repeatable algorithms. They're randomized planners, and so every time your robot plans, it produces a different solution, as you've probably seen, right? Just the diversity of solutions is huge. And then I asked the question, like, why can't we, what keeps us from using trajectory optimizers? And more importantly, what is the invariance that we seek? Like, what invariance do we seek if we build a trajectory optimizer, right? And obviously you want to make sure that you seek coordinate invariance, you seek the invariance that if you and I, you work in feet and I work in meters and we write the same code, we should get the same trajectory, right? Because the topology of the space hasn't changed. It's just our description of the space. And so I sort of reached into old sort of algebraic topology work, and we invented this algorithm called CHOMP, which is like all kinds of cute things and interesting things. I also, one of the things that I loved about it is central to CHOMP is this idea of a signed distance field, which think of it as like distances that are radiating out of every obstacle, right? Positive distances radiate out, negative distances radiate in. You want to make sure that you don't penetrate into the obstacle, nor do you, and you want to stay as far away from it as possible. I actually used a very clever trick from back in my days writing game programming to come up with a very efficient algorithm for computing these sort of signed distance fields in arbitrary like Hilbert spaces. So I like that algorithm a lot because it ended up being like 15 lines of code that anybody could implement, but it was the correct 15 lines of code. And it was also something that was easily reproducible. I was recently talking to that's okay. I guess I can share this. I was recently talking to some folks from Cruise Automation, which is one of the self-driving car companies, and they called me because they run CHOMP on their self-driving cars, and they had a question about the algorithm. And so we spent an hour and a half, and this is like 15 years or 12 years since the algorithm was invented, and we spent an hour and a half like debugging their code because they were finding some like weird edge case. So I thought that was a fun algorithm. And I think the bottom line is like if I had to take a learning lesson from that, it is it's always important to question the status quo, not because it's cool to question the status quo and you're a rebel, but because it's important. Because every status quo is built upon like questioning some other previous status quo, right? And I think as scientists, it's our duty to keep questioning and keep sort of moving the rock forward. And I think the second point I want to make is that it's important to understand what your algorithm does, right? And it is important to continue to ask that question over and over again until you can actually write down what your algorithm does. there are so many algorithms out there now that even their inventors don't know what their algorithms do. What is the invariance you seek? What happens when you change stuff, right? And sometimes you think of it as a feature, not a bug, but it's really a bug, right? Most of my algorithms are about 15 lines of code, but they are the right 15 lines of code that came out of like several years of distilling. So that's one. I mean, if I had to pick another one, sorry, I can pause and take questions here too for anyone. Have any of you read the Chomp paper yet?
I will monitor the question.
Okay, sounds good. The other one that I really like is actually something that you and I worked on, which is robot-assisted feeding. It's a project, not an algorithm. And personally, I like to think of working on two things. One are sort of cross-cutting algorithms that work across different projects, but also I like picking the sort of North Star projects. I want to be able to feed someone a plate full of food, right? It's very simple. It's the goal that we have, and it's incredibly hard. And I love having both these projects as well as these algorithms that are sort of running through my lab, because it compels us not only to invent new algorithms, but also deploy them in end-to-end systems and understand their interaction between other systems. I mean, you've all written code, and you've all written code with others, and you think your little module, you know, you test it very nicely, you run all of your unit tests, you even maybe run some integration tests. And then it's only when the rubber meets the road where like your piece of code and my piece of code all work together that most interesting challenges happen, right? Things never work for the first time you try it. But I think robot-assisted feeding is something that I truly care about very passionately, because it's important for us to build robots that actually help people, not make, you know, able-bodied people more lazy, which is sort of what most robots do these days. And I also think that it's an incredibly challenging robotics problem. It's a hard manipulation problem. It's a hard human-robot interaction problem. And it's a gift that keeps on giving, right? Like, I feel like I always want to work on things that help me learn. I'm constantly thinking of like, what is the next muscle I want to grow so that I get better? And I feel like robot-assisted feeding is one of those projects that every time I talk to you, or every time I talk to one of our users, I learn a lot about like what I should be doing and what the true meaning of building robots is, which is to create social good. And I'm the first to admit that like nothing that I do will ever be sufficient for that, but that doesn't mean we shouldn't try, right? We should continue to keep trying. So those are two children I picked. I love all the other children too.
Awesome. This is very, this is awesome. Okay. The next question I have is basically, so what is the most beautiful example of human or animal manipulation demonstration that you have seen?
Wow. That's really interesting. Actually, I can give you two examples like off the top of my head. And this is maybe it gives you a window into my thinking as well. But I showed up at the Robotics Institute. I was 19 years old, and I was like super arrogant and like I was ready to change the world, right? And I had my first meeting with my PhD advisors. And they were like two incredibly laid back people who were just not ready to deal with a 19-year-old Indian kid. And the first thing they showed me was this video of a dung beetle creating and rolling a ball of dung, right? And it is just the most interesting and sort of glorious thing that I'd seen. And they were saying that like, hey, Sidd, you should go build a robot that like does this. And in a very weird way, like I found it very challenging and interesting. And I think that what was fascinating about it, and that ended up being my master's thesis and ended up being its own sort of subfield of work, was understanding the duality between locomotion and manipulation, right? Like manipulation is, in some ways, you can think of locomotion as manipulating the earth. And you can think of manipulation as like walking along the object, right? There's all of this work on finger gating and other stuff that came after what the stuff that we did. And so I think I asked the question, if your robot only had wheels and nothing else, and no arms per se, it was just a mobile robot, like what could it manipulate? Like what could it do? Like a dung beetle doesn't have any specialized arms, but yet its entire existence depends critically on its ability to manipulate dexterously, right? But yet evolution never compelled it to like sprout a couple of arms, right? Because what it was able to do with its feet was sufficient, right? So it was simplicity and sufficiency, which I thought was really, really interesting. So I think from a nature point of view, I find that to be super, super fascinating. I think if I had to draw another example, I think obviously all of us think our kids are awesome and remarkable. This is unfortunate fact of life. We're sort of biologically tuned to do that, but I think recently I've been watching my son get better and better at playing the piano. And I find that learning process itself to be incredibly fascinating. Like when we go back and look at videos, and we have this like mildly crappy keyboard piano at home, and I guess I should invest in getting him a better piano. But what's really fascinating is how the human and the piano become one device, right? Like you watch him play now, and he's able to get these tones, this tonality out of the piano. It's not binary anymore, but it's just this, like, it turns into this analog rendition of music, right? He's able to turn something that seemed like a binary task, even like a year ago, into this sort of rich analog experience of being able to coax this, like, I don't know, a couple of $100 piano into producing these sounds that sound like, human, organic, analog, right? Reflect his mood even. Like sometimes he is angry and he goes and plays the piano and you can sense that there's this like big notes that are coming out, and sometimes he's happy and sometimes he's sad. And I find that to be really fascinating. And you think that, like, oh yeah, we can build a robot that like just goes and like plinks the piano. And I've looked online for some of these things, but somehow there is this richness that the human fingers and the human emotion is able to convey onto a piano that I am still yet to see, right, from robotics. And I think that to me, I find, if I were to work on the next thing, I think I would try to formalize that in some way. Like, how is it that a 10-year-old kid is able to? I'm sure many of you also play various instruments, and maybe you can sort of empathize with that, which is just the ability to extract like tonality out of this sort of very, very simple device.
It's fascinating, and that actually leads me to my next question, which is, what is the robot counterpart of this? Like, what would be like the most fascinating robot manipulation demonstration that you have seen, whether it's from your like own lab or somewhere else?
Yeah, that's interesting. I think I think the demonstrations that I've seen that I find, I mean, I'm gonna, like, as a roboticist, right? All I see are the mistakes, right? Like anytime I see a robot video, I'm like, I know how you hacked that. Like I totally know how you hacked that one. Like I know I know what's happening here, because like I've seen like robots for most of my life that like I can tell what parts of it are hacked in what ways. I think that one of the things like early on that I was super impressed with was, there's this team in Waseda University in Japan that builds these like very, very, very high speed manipulators, right? A high speed hand that moves so fast that you can't even see it moving. And they did this coin trick, where you put a coin on one of the between two fingers, and it's able to sort of move the coin through the fingers to the other side. Of course, like a lot of it was, I'm sure, a lot of trial and error. And like, if you look at the code, I'm sure it has a bunch of like, constants in there that even if you change by a 100th will break everything. But I found that to be remarkable because I just didn't expect that. I just didn't expect a robot to be able to do that. Like, it's just like, wow. And I saw it live, and I had to just sort of play it, ask them to do it over and over again, because it just seemed just so unreal, right? It just didn't seem like it was in this realm of reality. I guess like you may have seen like some Boston Dynamics robots, exhibiting things like that also. I find those also to be inspiring, but I know too much about how they work to be like as I'd be, since I work with a lot of these people. But I thought that was really fascinating. That it showed me something that I just never thought was possible. And that was like almost 10 to 15 years ago, and I don't think I've seen anything as impressive even since.
Awesome. We actually have an audience question. Yeah.
So I think this is related to the idea you were just discussing. Every time we look in the code of all these robots and how they develop them, we're going to find a bunch of constants which are just like, they're so hyper-tuned that you change them a little bit and it's over, right? So how is even task generalizability or environmental generalizability even ever going to be possible if that's like in every single situation we're going to have constants that we're trying to tune that if you don't tune correctly, it's just over, right? Like, so like, what is the way forward beyond that? Like, how do you go from that to, well, being able to generalize like we do, like as humans?
Yeah, it's a great question. I mean, I think I want to talk about like sort of two variants of what you said, right? One of them is that oftentimes you work in a closed world where even though there is some variability in your inputs, you know what that variability could be, right? Even though you may not have seen all the variability, at least you can define the space of variability that you can encounter, right? And then you build algorithms, you build controllers that address that variability that you expect to see. A lot of problems that I work on at Amazon are in an open world, right, where you can't even predict what variability you expect to see, right? I build the AI that delivers you your packages at home, and it's very simple. But I have to deal with over 20 million items that you can purchase at Amazon. And imagine having to manipulate over 20 million items carefully without damaging them and packaging them and all of that. And that number is increasing by 200,000 every week, right? So it's just, even if you look at like the sub 5 pound category that we need to manipulate with our robot arms. So I think that a lot of what, so the main joy, at least for me in robotics, is not going from the 0 to 60, which sort of deals with all the sort of the happy path, we call it, like all the things that can go right, but really is in being able to go from the 6. I mean, it's important to get to 60, but really where the most joy is for me is from going from 60 to 80 and 80 to 90, because that's where you are really challenged as a full stack roboticist, right? Like you can get away getting things from 0 to 60 without knowing parts of the other stack or how they interact. But if you really want performance systems, then you have to go from 60 to 80. There's another interesting question of like, what is the incentive to go from 60 to 80? And I think for me, it's twofold, right? Like one is like there is an intrinsic incentive for me. I hate robots sucking. And that's just personally annoying to me when my robots don't do well, and Tapo can attest to that. And so for me, it's like incredibly important that we do the right thing. And so even if that doesn't mean that we end up, even if it means we don't end up writing as many papers. I think the second piece is that, like, if you really want to change the status quo, if you really want to be the person who's pushing the frontiers of robotics, you should go and be in places that challenge what exists right now. And I think like that only exists like beyond the 60%, right? You could spend the rest of your academic career making pretty YouTube videos of taking things from 0 to 60, and that can be a very successful academic career, but I don't think it's going to be transformative, right? It's not going to transform the way we do robotics and we think of robotics. And the other thing that you should always think about is that like the next student who comes along should not have to start with the same like crappy system that you had to work with, right? You want to make sure that you're putting things out into the world such that you're taking steps and people can stand on your shoulders to tackle the even harder problems, right? So I think whenever my robots don't work, I actually love that, because then it starts teaching me what I need to focus on to make that right. And I don't find, I was talking to somebody who said like, oh, engineering is just elbow grease. You know, scientists don't have to think about engineering. And I completely disagree with that, right? Like I'm a roboticist, I'll do anything. Like I'll build robots, I'll write code, I'll do anything to get robots to work. And if you have that sense of ownership about your system, that's when the most interesting work comes about.
Awesome. Skylar, you have another question here.
I just wanted to go back to what you said about the needle and ask if evolutionary principles ever inform your design process, and if so, what project would you say that's most true for?
Yeah, I think that I'm always inspired by what I see humans able to do as well as and animals able to do. Like you know, I spent a bunch of time when my wife was a PhD student, like staring at like fruit flies and trying to convince her that she should use computer vision so that we didn't have to go to the lab at 2 in the morning to check whether the fruit flies had like green eyes or red eyes or something. But I do find that to be very inspiring. I think one thing I would caveat and say that like it's important to formalize that also, right? Like I think that a lot of this, like, you know, even if you look at like evolutionary algorithms, for example, like they're actually based upon some very solid foundations of like gradient-free optimizers, black box optimizers. Like there's a lot of work in gradient-free optimization that you can lean on. And I think sometimes we forget that evolution is also running an algorithm, right? Even though it has some randomization to it. And so it's important to sort of write down carefully what's going on. I mean, in many ways, this is what inspired me to get into human robot interaction. This is like many years ago, because I went to my first human robotic interaction conference and I saw very, very interesting concepts described qualitatively, like on curiosity, of trust, of legibility, and all of those things. And I was like, well, surely we should be able to write this down in mathematics. Otherwise, like we're never going to be able to put that code on a robot. You know, you can't whisper into your robot's ears what it needs to do. You have to write code. And so that started me on an entire like new area of algorithmic human robot interaction, because I just wanted to make sure that we could write math about what was going on.
Awesome. So Sid, there is an audience question, pre-submitted question, which is related to what we were saying before. So somebody asked, like, as a robotics graduate student, how should one balance between open source code contributions to libraries such as ROS, OMPL, Aikido, etc., and research?
I can give you my impression of it, and you know, obviously, like you should take it as a data point in your existence. I think that like my own personal philosophy is that who you are is reflected in everything that you do. The paper that you write, the theorem that you prove, as Tapo will attest, like the font size of and the marker size that you use in your figure, and the thickness of the line, the colors that you use, and in the code that you write, right? Like I think that like you should think of yourself as, you should think of all of your artifacts as representing who you are and what you stand for. right? And so if you choose to write, open source code, you should choose to write it with the same level of integrity and attention that you choose to write your research paper, right? And I think that's very, very important. Like I think we've all downloaded and forked repos, and some of them we've been so incredibly grateful for because someone went out of their way to make sure that like they addressed my needs, not just their needs but my needs. Some others were like, what is this garbage here, right? And you end up rewriting all of that code because you're like, well, this is just there because it was supposed to be there. So I think from my point of view, I think my meta point is that like whatever you choose to do, think of it as a representation of you, who you are and who you want to be, and do the best you put into it the same amount of attention that you put otherwise. I've also like strongly believed that like it's important to get peer feedback for anything that you do, right? And so I think in terms of my own algorithms, they fall into essentially like one of two buckets. Either they are described and written so simply that it takes a third party very little effort to replicate my algorithm, right? Like, if you look at like lazy search or any of these other things, like I can explain the concept to you and it's like a 4-line tweak to your like existing A-star algorithm, right? Or they fall into the bucket of like, not everything falls into that bucket, right? Like I'm not saying that everything should be 10 lines of code. If it falls into the bucket of like, this is complicated, then I try very hard to make sure that someone else doesn't have to go through the pain of dealing with all the corner cases that I had to go through so that I could render my work to be effective. And in those cases, I actually take a lot of attention to release the code in such a way that it is usable for others, right? So I think a lot of it depends on like how you want the world to be able to use what you're doing. And the world pays back in so many ways, right? Like way one is you see your stuff being used by others in places that you never thought about, right? Like this constantly amazes me that like people use my algorithms in like all kinds of places. And the other is that the feedback that they provide, like, for example, like, hey, Sidd, like your algorithm doesn't do that well in like SE3, like what's up with that? That is incredibly useful for me to go and introspect my algorithm again and ask like, okay, why is this happening, right? So it's almost like you're getting free expert advice, and why would one not want that, right? It seems like that would be that's something that one should always seek.
So I have another question based on this idea of being a full stack roboticist. A lot of like robotics is a very wide like field in general, right? There's a whole lot when it comes to like the physics of it, the mechanics, just like the base level code of the robot, planning, control, high level learning, decision making, all of that, right? Like to do stuff as a full stack roboticist, you have to have knowledge in all those fields. Like, how do you balance learning these different concepts and like keeping up with everything, and as along with doing your own work? Like,
yeah, I think a lot of it depends on, it comes down to prioritization. I say no to more things than I say yes to. I say no to a lot of things. I also, in general, only work 9 to 5, and I like to cook. I like to play sports. I like hanging out with my family. I don't particularly. I don't have a fear of missing out of anything. In general, my feeling is if they want me, they'll come and ask me. Otherwise, they're in good shape. And I think to your point of like, there's just so much to do and so much to learn. In general, I pick my battles, and I try to go as deep as I can on something. Like whatever I do, I want to be the best in the world at. And that's my North Star. I almost am never the best in the world at anything, but at least like that's always my goal, right? Like I've started playing tennis again. I used to play tennis competitively when I was young, and I want to be the best tennis player in Seattle. And yeah, I've got a ways to go, but that's always my goal, right? Like I have no no intentions otherwise. And if that means that I have to like put in the effort to do it, and if I have to stop running, which I had to do, then I'm like, okay, I'm cool with that. I think the other thing is also that like I always believe in being able to experiment and creating enough scaffolding such that it's easy for you to experiment. Like, a lot of these frameworks that we've written, like OpenRay or Dart, they were written because we wanted to make sure that it was easy for us to test out new ideas, right? One thing that I used to do, a while back, and I still do at Amazon, is I ask the question, how much effort is it for us to test out an idea? Like, write it down in like human hours, right? When you have a new idea and you want to like really test it out, and then ask yourself, well, the next time I do it, how can I make that 50% less, right? Because unless you have the ability to test out your ideas, you're not going to be able to disconfirm your beliefs, right? Like, most of research is about disconfirming beliefs. It's not about confirming beliefs. It's actually about disconfirming beliefs, right? Because you're like, oh, I think this is how it works. And then you realize, that was totally stupid. That's not how it works. And then you're like, oh, well, what's the next thing that I think it works? And you're like, well, that was totally stupid. That's not how it works. And I think that's how, and then of course, like in the end, you present your paper as like, I woke up one morning and thought of the answer. I'm glorious. But really, what happens is that like you do a bunch of wrong things, but you have the scaffolding set up such that you can disconfirm your beliefs until you whittle it down to the thing that you just cannot disconfirm. And then at that point, you realize, I guess this is the truth. Like, I guess this is it. So I think that would be my recommendation, is just like pick one or two things that you want to be really good at, and be good at them, and also like go and like seek out experts and build systems. Like, I still use some of the code that I wrote like 15 years ago, because it's pretty reasonably well written and it still works. And I remember when I wrote this code a long time ago, I was like, well, I better make it such that people can use it in the future. And so I think you wanna bet on yourself and continue to build that muscle.
I wanted to say something, Sid. I remember when I was a postdoc. I mean, you told now that 9 to 5, but I've seen you emailing like 4 a.m., 5 a.m.
That is true. I do sleep very little, so I must say, I'm usually up by 4 in the morning. Yeah, I think that there's a background process in me that continues to work, no matter whether I'm awake or asleep. But certainly the foreground process only works like 9 a.m. to 5 p.m. But you're right. Yes, I must.
Yeah. I actually had a question about the same thing, and like, do you think that you working 9 to 5 is a function of is mostly a function of where you are in your career? Like, do you think as a grad student you didn't do that, or or like as a tenure track pre-tenure professor you didn't do that, but
Yeah.
now
that I'm old.
I mean, yeah, you're great, you're accomplished, you're like successful, you know?
It's a great question, and let me answer honestly, right? Like, I think that all of your tools sharpen and refine over time, right? My tools for time management, my tools for decision making, all sharpened and refined over time. I also learned more and more about who I wanted to be as I got older, right? It's just like, there were all kinds of things I wanted to be, and it was important that I sort of went through that process myself. I think one thing I would also say is that, like, from when I joined as a PhD student to now, I am very ambitious and I am very impatient. And I hold myself and everybody around me to a very high standard. And I think, I don't know, at least I hold myself, which is what I can say. And I think that the perspective of like, I think one thing that works for me is that like I've always loved cooking, and I've always played some competitive sport all my life. And those occupy a fair bit of my time. I cook for at least an hour every day, and I play at least an hour, hour and a half every day. And so that naturally like shrinks time. I think one of the things that I've gotten better at over time is just being more efficient with everything that I do, right? And part of that comes from experience. Like I can read a paper, and I am faster at being able to understand its key insight than I used to be. But I think that comes from honing that skill, right? Like you have to hone the skill very deliberately. I don't know if you know about, there's this concept of deliberate practice, which is that you can drive a car for several hours every day, but you're still never going to be a race car driver because you're not deliberately practicing. You have to, every time you practice, you have to put yourself in a situation that makes you uncomfortable such that you can get better. And if you don't do that, it's not just the amount of time you practice that matters, but really how you practice, right? And so whenever I'm in a meeting, I'm always putting myself into a state where I'm like, okay, like what am I getting here? Like how can I be effective? Like how do I push myself out of the comfort state that I'm in? And I think and I think that intensity is critical for you to be better such that it gets easier. I think another thing that I used to do, it's funny because like, I think I was a very unproductive grad student. I don't know how I got my job after grad school. I used to just sort of, I loved robots, and I would just go around like building lots of robots. I wrote a SIGGRAPH paper as a grad student on some random thing. I wrote a bunch of other just sort of random papers. And I built a robot inspired by a dung beetle. So it's not like I was very focused. But I think that I think junior faculty, like being junior faculty, was hard because there's a bunch of like extra additional pressure that comes about, and until I could like shake that off. I was also a junior faculty in the school in the same university that I was a grad student at. So I suddenly started sitting in meetings with all of my teachers around me, and so you wanna sound smart with them. And I think it took me a couple of years to sort of get equilibrated to that. But I think in general, working on meaningful things that enrich you almost always pays off in the long run. And I think the other thing I would say is that the people who are in robotics who long enough know who the good people are, right? Like I think this is the thing that like you should always keep in mind, is that like it's not a function of the number of papers. It's just a function of like who delivers on the promises that they make, right? Like what are the promises you're making to the world, and how are you delivering on those? And they don't have to be big, but as long as you're delivering on them.
Awesome. So, a question. Yeah.
So, I'm actually curious now that you're talking about your PhD, like when you were a PhD, and like one of the questions I have is, how do you deal with the concept of like ideas and projects failing and like things not working out? Like, how do you work beyond that? Like, what do you do to get like? Because from what I hear, very often that is a thing, right? Like ideas fail, projects fail. Like, how do you get beyond that?
Yeah, I think it's important to. It's a tough one. Like I think a couple of things. That like one is I always find I find adversity challenge exciting. Like I find it delicious. I find it if something is hard, I always think of it as like, well, that means it's important. Maybe it's the way I trick my mind into doing adverse things. But I think the other point is to really ask why, right? Like why isn't it working? And oftentimes that why leads you to a new direction, right? And I think this is an important life lesson also, right? Like it's just that things will almost never work the way you want them to work. And a lot of what we need to do is to have the mental flexibility to ask why, and the sort of the belief that you'll find the answer, right? Like I think this is what I struggle largely with some of the students that I work with is if you don't have that belief that it's going to work, then that's a self-fulfilling prophecy. It won't work, right? Because we are fundamentally working on things that are really hard and fundamentally working on things that like require you to have a tremendous amount of faith to get it work and to get it work for real, right? Like I think there's numerous times where you have the wish to just hack it or like, oh, let's just like add a few more things. And like I've always believed in like the long play, right? Which is that like, no, we should figure out why it's happening because surely there's a way to understand that. So I think I fail a lot and I either fail fast, like I fail as fast as possible, which is really important. And I'm very unemotional about like discarding things that fail. I'm like, okay, like that just failed. And then always ask the question of for any failure, like, why is it happening? Like, what's going on? Like, why? And that often leads you to a state of sort of new discovery.
I remember Sidd used to tell us that one of the very important qualities that he looks at in a student is the student bold? Like, can they take up, like, do they have the belief to take up hard problems and know that they will be able to solve, even if they don't know the solution now, but they are working towards solving. Yes, Brandon.
Oh, I was wondering, like, can you tell us more a bit about your process of coming up with new project ideas?
Sure. Again, like I want to say that like this is again like one example, and obviously like everybody has a different way of doing that. A lot of my projects come in sort of at least ideas come in two different ways, and they're both linked in terms of observation, right? One way in which a lot of my ideas have come about is observing the natural world and asking like why is this happening, right? Like whether it's the way your fingers curl to pick up a coffee mug, or the way you sort of like make eye contact or not make eye contact when you're sort of talking to a person, just a social dance. And then I try to ask myself like, okay, like why is this happening? I even like a lot of the times I'll try to explain it to my kids, or I'll try to explain it to somebody. I like giving talks, and and a lot of my talks are about like the questions that I'm asking more than any of the answers that I might have. So really being curious about phenomena and asking how those phenomena can be sort of created by a robot. I think the other place, which I highly recommend, is to read papers and to be curious about things that those papers themselves are unable to explain. So a lot of my work, for example, in lazy search, came out because of one figure in one paper that I was reading, which was just this like stray figure that sometimes you have a little bit of space, like, oh, let's toss a figure in there, shall we? And it was one of those figures. It wasn't even referenced in the paper. And I was looking at it and I was like, oh my God, like what the hell is going on? Because it basically, that figure showed that most of planning time for robots is dominated by collision checking. Like it's not the search, but it's the collision checking. And the paper sort of had a bar graph, the usual bar graph of like, hey, we profiled our code and like 4% of our time is spent this, 3% of that, and like 73% is spent collision checking. And then I was like, well, like surely somebody must have written something about like how you minimize collision checking in search. And it turned out that nobody had. And I was like, okay, I guess I'll have to invent that algorithm. And then we ended up solving an open problem in search that had been open for 40 years with a very, very simple algorithm. And so I think from that point of view, when you read a paper and you observe something that like neither the authors of the paper nor you are able to explain, then you'd be like, oh, well, what the hell's going on here? Like, I better try to like figure that out. So I think that's why I love reading papers, because not only they tell me where the state of the art is, but they also tell me what the state of the art is as yet incapable of explaining. Like what is the frontier, and that helps me a lot. Another thing I would say very quickly is if you are unable to replicate some result in a paper, that almost always suggests that there's something deeper going on. Some of my work on, so we did this work on manifold particle filtering, which is like generalizing sequential importance sampling and resampling particle filters to constrained manifolds. And a lot of that happened because I had an undergrad working on doing particle filtering, like you all know how to do, for pushing. And they were constantly struggling with getting the filter to converge, even for really, really simple problems. And so they tried doing a bunch of hacks, and I was like, no, like, let's at least like understand why this really simple algorithm is like failing so miserably in this seemingly simple problem. And that ended up being like an entire area of research. So I think sort of your inability to replicate some work or some piece of work means that there's something fundamental that's happening in there that is worthwhile exploring. So having a good spidey sense is important. Like you have to have a good spidey sense for like, something weird is happening, and always sort of follow that. 4 times out of 10, that spidey sense will just be like, I guess it's weird. But the other 6 times out of 10, it'll be something that's actually really meaningful. The thing that I try to avoid doing, partly because I'm incredibly lazy, is that like I try not to follow fads, right? Like if someone's doing something just because it's cool, I'm like, okay, why don't you do it? I'll just use the output of your work for the stuff that I'm doing. But like I always try to have a spidey sense of like where things are sort of don't fit perfectly.
So Sid, I wanted to ask a couple of questions submitted before the class by audience. So for this question, I would ask you to wear your professor hat and then Amazon Robotics director hat. And the question is, what skills are important to master robot manipulation research, let's say in academia, and versus what skills are considered important to have a career in robot manipulation in industries such as Amazon Robotics?
Yeah, it's a great question. I mean, I think what's common to both of them is your ability to build systems that demonstrate capability, right? Like whether it's being a researcher or whether it's in industry. For example, like Tapo and I could not have thought about feeding and done it all in simulation or done it all like in theory. You got to go build a feeding robot. And I think like we both agree that like we learned a lot just from the process of building that robot. Is it the best feeding robot ever? Definitely not. But it's certainly something that helps us like stair-step our way to greater discovery and greater understanding. So I think manipulation is about show me what you can do and show me what your robot can do. So it's important to have that skill to actually create that physical artifact. I think in terms of like where they might differ, like being an academic and being a researcher in an industry, I think it's largely around sort of where you want to be in terms of learning the adjacent skills, right? Like, so I run a business at Amazon. I understand very carefully the financials of what it means to take my solution and put it in a product. I understand what it means to scale that. It is a science itself, right? I understand and I make decisions of what I need to do based both on sort of the intellectual curiosity and the ability, but also on the business needs, right? There's certain business needs that I have. And so I think part of that is sort of like, what adjacent skills do you want to learn? Is it finance? Is it like HR? Is it management? Is it, understanding how to work with contract manufacturers? and how excited you are about that, right? And I think that being a roboticist is necessary but not sufficient to being successful in industry, right? And so you need to have all of those adjacent skills to be successful. And I think like one of the things that's like really important in to be a successful academic in robotics or manipulation is your ability to teach, right? Like your ability to, and that is related to your ability to simplify, right? In industry, as long as it works, it doesn't have to be simple. Like it just has to work. Whereas I think what's important in academia is that not only does it have to work, you have to be able to tell me why it works. You have to be able to explain to me why it works. And you have to be able to explain that in such a clear way that I am able to understand it as fast as possible. So I think that additional skill is really important.
Okay, there's another question from the audience. But they're saying, can progress in robot manipulation be accelerated by better benchmarking tasks and more realistic simulation environments?
So first of all, I want to say that there's been tremendous progress in robotic manipulation over the past decade. Like I think the progress has been exponential. I'm super excited to be in this space. And I think part of that success has been the ability to democratize robotic manipulation a little bit more, both through the availability and accessibility of reasonable simulation environments, and also in the availability and accessibility of robot hardware, right? Back when I started my PhD, I had to build my own robot arm because there weren't any robot arms around. Right? I had to write my own like IEEE 1394 camera driver to pull out the bits out of my 1394 camera. And I think a lot of that is much easier now, right? Like we have the ability to get bootstrapped much faster. In terms of sort of benchmarking and software tools, I think yes to both, right? I think that you know, so I've been working on some efforts to try and benchmark robotics, and I see that not as like, oh, I'm standing on this pedestal telling you all what you should be working on, but really as like an ability to share results honestly across different groups, right? And I think we're a fair ways away from doing that, even in simulation in robotics. And I think simulation tools are super valuable. I totally agree. I think as long as you're able to use them as a stepping stone for building real robotic systems, right? Because you know simulations are doomed to succeed, but real robots are the ones that like are the most sort of finicky and interesting. So I think they're both super useful. But I do think that we're in a fairly golden age of robotics where there is such there's much lower barriers to accessibility of robot hardware than there ever has been, and it'll continue, right? Like I do want the next Sidd who grows up in India to have actually worked on a robot before they started their PhD.
Awesome. Another question related to this is, so what do you think is the future of robotics? Like what are the most promising areas in this, and what are the biggest bottlenecks, like biggest challenges that people should tackle, or like students and researchers should tackle?
Oh, that's a tough one. First of all, I'd say you are the future of robotics, all of you over here, and you are the ones who should be telling me what I should be working on, since you're the next generation. I think that there's a lot of promise to robotics, and I think that we need to start delivering so that you know when people come calling for their you know for their checks. And I think that it is really up to us to make sure that we sort of deliver on that promise. I think for me, something that's really exciting, what is personally fulfilling to me? Personally fulfilling to me is the ability to get robots actually out in the real world, dealing with the sort of open world challenges that we're facing, right? Right now, a lot of my work at Amazon is focusing on continual learning, the ability to be able to identify when your data distribution is shifting and to be able to actually adapt to that, like whether you're doing important sampling and retraining your models and things like that. And I find that really fascinating to be able to close the loop with that. And also, I think that it's really important to democratize robotics. it's important such that like our robots are so effortless to use that they can be used anywhere in the world, right? And I think that's super interesting. From a technical point of view, I think that there's still excuse me, a lot of open work in manipulating deformable items, and I think that that's whether it's food or whether it's anything else. And I think it's one of those places where our simulators aren't particularly good, and so we need to find different proxies for being able to manipulate deformable items. I think what's the part that's really interesting about deformable items like food is even defining state is very difficult. Like, what does it mean to define the state of a bowl of spaghetti, right? Is it the location of every single spaghetti strand? And I think like those kinds of questions are interesting and important to think about. It's just about how do you define state in spaces where you have such high dimensional things happening, but only a very small subspace of those are actually relevant.
Awesome. I think so. I'll ask maybe one last question, and then if you have any other questions, you can go ahead. So Sid, what are some of the best advice that you have when you were a student, and some advice that you want to give to the next generation of students in this?
Yikes. I think I can tell you like one anecdote which happened right when I joined my PhD, which was I wrote my first paper and I was super excited about it, and I wanted to submit it to my like first ICRA conference. By the way, I'm going to go to my 20th ICRA, this in a week or so. So I am that old, and so one of my advisors is like incredibly soft-spoken human called Michael Erdman. He looked at that paper and he said, I want you to take my name off of this paper before submitting it because it's not worth my name. And I was really shocked, and I said like, wow, like I reacted and I said like, look, I'm not going to submit this paper without your name on it. Like, I don't want to submit something that like you don't want to put your name on it. And he made the point that like, look, like you're writing this paper not for yourself, but you're writing it for history. You want history to be able to read this paper and say, oh, that was a reasonable paper. And that really stuck with me. Like, I am glad to say I wrote a lot more papers with him, and he didn't bring this up ever again. But I'm really grateful that he brought it up the first paper I wrote, because it told me very clearly like what the standards are that I should expect. Right? It's just that you're not in it to be better than the bottom. You're not in it to be better than your peers. You're in it to be historically good, right? Like that's who you want to be. You want to be historically good. And yeah, I know it may sound like, no, never, that's not possible, but you gotta aim there, right? And then the process will then follow to make that happen. The other piece of advice that I can give is that I started this like sometime early on in my career, and I continue to do it. Every time I read a paper, I write a short paragraph about it in a doc. Right now, I just like email it to myself. And I have several thousands of those by now. And it's super useful because, we've all been there where you read a paper and you get it. And then 2 months later, you read the paper and you're like, I don't understand what the hell is going on. I don't understand anything here. And so whenever that happens, I go back to my like short summary and like, that was the point of this paper. So I think being able to build mechanisms such that you are more effective and you don't end up having to replicate or relitigate things that you already learned before is really important. So writing down your meeting notes, writing down your ideas, writing down things where it is searchable is really, really important.
Awesome. Thank you, Sid. Any last questions? Yes.
I have a question about like this is more related to the like how you manage time and stuff. Like you told that you work, like I'm going back again to 9 to 5 thing. Like, you can like you're working from 9 to 5 and then you spend time cooking and other stuff like playing the sport. Like still like you were saying you sometimes sleep at 4 o'clock or wake up at 4 o'clock and stuff like that. my question is, how do you what is the main secret or anything like that which helps you manage all that? Is it like being more efficient in your tasks, or is it that with time your skills get sharpened? Like, what is it exactly? I just wanted some insight.
I don't know. First of all, like we should ask. I'm going to put this question to Tabo and ask, like, am I efficient? You can be very honest about that. Like, maybe I just suck at everything.
Oh my God. No, I think, I mean, when I was in Sidd's lab, Sidd used to tell this is that, you just need to be very disciplined about your time. Sidd also shared, which I do this with my lab, my students, concept of deep work and things like that. So you need to first know in a particular day, what part of the day you are, very active in thinking kind of thing, where part you are still awake, but you are not that, you cannot think. And then you should be very disciplined about, okay, that part I need to do this kind of work where I need to think about research and things like that. In other parts, I need to reply to emails or do some stuff. And you need to be very disciplined about this. If you're not disciplined, if you don't follow this properly, then again, this system will not work. So yeah, I think it basically comes down to discipline. And another thing Sidd used to say is that even if you're not actively working, you should get to a point, especially for your research, is that you are thinking about it. So you get up in the morning, that's what comes to your mind. Or you do some activity, that's what comes to your mind. And I've told this to say, like after I started working on feeding, it has completely changed my way of how I see when I see people eating and I eat myself. Like I always think about, what are the different strategies people are using to eat? So that's another thing. And that on the back of the mind, it just goes on. That's how you keep thinking about ideas and things like that. So discipline and that, yeah, that's probably, I think. I don't know, Sidd, what do you think?
Yeah, I completely agree with all of that. I think for me, it's always like I'm pretty intense in whatever I do, and whatever I choose not to do, I just don't think about it at all. Right?
Yeah.
Like and I think it's important to have both of those so that you don't burn out, right? Like you have to whatever you do, like I prepared for this meeting, I'm here, I'm present, I'm not doing anything else, and then when I'm after my next meeting in 15 minutes, I'll be like fully present there, right? And I think it's a skill that you just need to develop. And I also, like, oftentimes I just won't be in meetings where I don't have to do that. And that's it. Like I think some of my meetings with my students or with Apple have been for the explicit purpose of just shooting the breeze. And I'm cool with that too, right? Like, if that 30-minute chunk is about like, we will shoot the breeze, then I will shoot the breeze, hopefully with a lot of effectiveness. And so I think it's just important, like Tabo said, like I usually like wake up every morning, I look at my calendar, I'm like, okay, I know here are the things that I need to do, and I'm ready for them, right? And I think really, like, your time is all that you have, and you want to make sure that you are well prepared, and also you're balancing your like tactical things that you need to do, the shallow work that you need to do, with the strategic thing that you need to do, that is the deep work, right? Like you can spend all of your time busy, but you won't have actually done anything, right? If you're just like answering emails or doing various things, then you're just spending like these like tidbits doing like shallow things. Whereas really what you want to do is say like, okay, I'm going to do something which involves like a large amount of my cycles and really enriches me such that I can be better. And that's the deep work that you need to commit to doing at some point, right? Like, it doesn't have to be every day, but I certainly have like chunks of time blocked off in my calendar for just that.
Awesome. This was amazing, Sidd. I mean, thank you so much for taking the time out of your busy schedule for this. I think we all had a very rewarding experience. Thank you so
Cool.
much.
Well, thank you, everyone. And I'll see some of you at ICRA. Otherwise, I'm sure I'll see you around. Take care.
Bye. For students, so yeah, this is it for robot manipulation. course. For students who are registered in the class, please fill out the course eval survey. I would love to get your feedback on this because this is something we'll continue to offer. And I guess our final project thing is this Sunday at 2 p.m. There'll be food, pizza for everybody. So please come, and I'll see you there. It was great, learning from you. Awesome. Thank you.
Okay.